Hello, everybody. Testing 1, 2, 3. Testing 1, 2, 3. Start video. I bet that's what I want. Start video. Oh, look, we've got some customers already. We have Adam and Ben and Kristen. They're connecting. They are connecting. We have 5 minutes. We haven't really started yet. Good. And Calvin, we have Calvin. That's good. Connecting. I wonder if I can get my white. Yeah, there's my whiteboard. That's pretty good. Got a whiteboard now.
Hello, Mr. Griffin.
Hello. Yeah. Hey, Mohammed. Yeah. Good.
How are you?
Oh, not too bad. I'm kind of sleepy though. Need a nap. Is it okay with you guys if I just take a nap?
Sure. maybe after 2 o'clock.
Maybe after the class.
Yeah.
Good. Now let's see. We've got Adam and Ben and Kristen. Well, let me write down what I want to do with us today. Okay. I don't know if you remember, but I wanted you to work a problem just for fun. No points on this problem. But I wanted you to work, I think it was 1346. And so, yeah, we can go over it. It won't hurt us any. Today, I want us to do 1346. That'll be good in case we have something like that on our final someday. And then I want to talk about the rail gun. We'll talk about that here for a few minutes, and then I want to talk about, these are topics I want to talk about. I want to talk about the magnetic field inside a wire. I got a bunch of different topics here, and then we'll be lucky to get to all these. Oh yeah, force between wires. Now we've studied that, but we probably should practice that. Yeah. It wouldn't hurt us to practice the force between wires, parallel wires. Well, there's a few topics, and I have some others that I want to get to. We'll see how far we get. But the first topic is this 1346. And let's just go through that and make sure that we did that right. Let me find it here. Yeah, we're still early. It's only 3 till 1 here. And I'd like to get into chapter 14 even. Maybe we'll see. We'll see what we can do. We'll see if we can get into chapter 14. Okay, now let me find this 13. There it is, 1346. Okay, now right now, we're going to go through this 1346 in case we see another one like it someday, like on our final exam, for instance. Let's see. Let me see who else we got. Hey, Adam is here. Good deal, Adam. Glad you're here, buddy. I want to see who else is here. Yeah, oh, we got a good crowd. We have Kristen, Logan, Mark. How come Logan's on here twice?
I have one on my phone that I use for video, and then I have one on my computer because it's easier for me to see everything on my computer. And
Okay.
if it's on my computer, then I can lock you into one place and I can see your stuff easier.
Wow, that is cool. And then there's Calvin and Zach, and well, we got a good crowd. Okay, now right now we are looking at 1346. Yeah, here it is. Okay, well let's go through this and make sure we can do this. We've got a conducting rod here, and somebody is pulling on it with a force F, 2 ohms, magnetic field into the board, equal to 0.25 Teslas. Those X's stand for magnetic field into the board. Okay. And what else do we know? We know the distance here is 4 centimeters or 0.04 meters. And we know anything else? Let me read it here. Yeah, it's moving 5 meters a second. This thing has a velocity of 5 meters a second. I think that's all we know. Okay, now you can use Faraday's law to get the voltage in this loop. This is our loop right here. You go ahead. I heard somebody. We can use Faraday's law to get the voltage in that loop. Usually they have an N there. But we don't need that stinking N because there's just one loop there. If you had 5, 10, or 100, you'd have to put it in there. The minus is to remind us of Lenz's law, which says something about the induced voltage creates a current that will create a magnetic field that will oppose the change in your magnetic flux. Lenz's law. We've talked about it, but by the time you get through plugging in what the flux is, which is B times the area of your loop, and notice that it's getting bigger. The loop is getting bigger as your conducting rod moves. It's a lot easier to use this thing called BLV. It's got a fancy name. It's called motional EMF. I think I gave that to you already. But you could read about it. It's in your chapter 13. And in this case, the voltage is going to be 0.25 Teslas, 0.04 meters, 5 meters a second. We're going to get our voltage now. I can't do that in my head. 0.25 times 0.04 times 5. I'm getting 0.05 volts.
Yes.
Yay, I heard a yes. Now we're going to get the current. Now here we have to think about this because the current is either going to go counterclockwise in this loop or it's going to go clockwise. Lenz's law says the flux is getting bigger because the area is getting bigger. So the current will have to go this way, counterclockwise. Because if you put your thumb along the current, your fingers will be coming out. That will oppose this increasing flux going in. So the current's counterclockwise. We figured that out. And I tell you what it's equal to. It's equal to your 0.05 volts divided by 2 ohm. Hey, I can do that in my head. I'm getting 0.025 amperes. So and it's counterclockwise. Do we have any comments or questions?
Nope.
We're okay. Excellent. All right, now what do they want us to do? Let me read this again here, just a second. And let's see, find the EMF, we did that. Induced current, we did that. Clockwise or counterclockwise, we did that. It's clockwise. No, that's counterclockwise. Then they want the force. There is, see that force there? We're going to get the force. Now the equation for that force, it's in your book someplace. It's called the Lorentz equation. It goes like this. You've seen this before too. I'm going to use a capital L. What's confusing, sometimes they use a little l. Sometimes they use a big L, but we're just not going to get stressed about it. Now this L is going straight up because that's the current. B is going into the board. And if you'll cross that L with that B, you will get a force going this way. This is your magnetic force. Well, now they've got a force there, but that's different. See, this is your magnetic force. It's going to the left, and it's equal to 0.025 amps times 0.04 meters times 0.25 Teslas. And we're going to get our force. Yeah, that's the magnetic force. See, that's opposing us. We're pulling on this thing, and there's a magnetic force that precisely equals what we're doing. If we're pulling real hard, it pulls back real hard. But anyway, at this kind of speed here, where our speed is 5 meters a second, I can't read my own writing. What's that little smear right there? I can't read it. I think it's supposed to say a V, maybe. I don't know.
Yeah, that was supposed to be
Yeah.
a V.
Yep.
Maybe that's supposed to be a V.
Yep. 5 meters per second. Yep.
Can't read my own writing. Okay. Or maybe it was an X. Maybe it was one of these X's for the magnetic field. Maybe that's what it was. Anyway, we're going to get that force now. Here it goes. 0.025, 0.04, 0.25. Well, I'm getting a real tiny force. I can't help it. I'm getting 2.5, 10 to the minus 4 newtons.
Yep.
Yay! So we have the magnetic force going to the left. This applied force, or external force, you could call it, is going to the right, and it will equal that. That will be the same amount, the 2.5. Now, if you wanted to be fancy-wancy about it, you can make this bigger and make that smaller and go 0.25 millinewtons. Now, isn't that cute? You can do that if you wanted. See what I did? I made that bigger. If you make that bigger, you got to make this smaller. Okay, now let's see what else we're supposed to do. Let me read this. It says here, what is the power? Okay, let's do that. Well, there's two formulas for power. One is electrical power. And it goes like this, I squared R. And the I is, where'd it go? Oh, there it is. 0.025 squared, and the R is 2. So let me do that. 0.025 squared times 2 ohms. I'm getting the electric power as 1.25 times 10 to the minus 3 watts. But there's another formula for power, and that's mechanical power. Somebody is pulling on this. They have a force, and mechanical power is force times velocity. Well, what's the force? Here we go. Here's the force. It's 2.5 times 10 to the minus 4. And the velocity is 5. So I'm going to multiply this by 5. 2.5 e to the minus 4 times 5. I'm getting mechanical power is 1.25 times 10 to the minus 3 watts. Ooh, that's good. They're both the same. We're generating electrical power is what we're doing by pulling this rod along that those rails. We're creating a current, and we're warming that resistor up. It's getting hot, and it's producing power equal to the power that we are inputting. So there's that problem that I asked you to do just for fun, no points. Now I put a problem on under content for points, for four points, and it's due Monday. If you go to content and then go to assessment and then click on assignment, you'll find that I've given you another, I'll count that. I'm learning how to grade your papers on Blackboard now. How about that? See, I can still learn stuff. All right, now I want to tell you, we just did that. And I put a little check mark on that. Did anyone have a comment or question about the problem 1346?
What kind of material should I be thinking about with that parallel conducting plate? Is that like a magnet, or is that just a random metal, or what is that made out of?
It's a conducting metal. It could be aluminum. It could be copper. Take your pick. But you really don't want a magnet. You don't want a magnet. You want a conducting metal. Okay, next topic. I wanted to mention to you about a rail gun, and they have a thing in your textbook here about rail guns. It's on page 598. If you want to, you could read up about rail guns. But let me just show you one. Let me erase some of this, and we'll show you a rail gun. I just need a little room here to operate. We'll just erase. We can keep this same thing here. 0.04 meters. But let me tell you the difference between this diagram and a rail gun. A rail gun has a battery here. Now I'm going to have to think about, I think I need my battery like this. If not, I'll fix it. Okay, now we got a battery there now. And hey, that's going to run the current the other way, isn't it? Here, let me get that current going the right way. That battery is going to send current clockwise. You can see that. It's going to get rid of that 2 ohms. Now, batteries do have internal resistance. There will be some internal resistance, not only from the battery, but from the connecting rod and even from the wires. Did you know wires have resistance? Haven't we done a little bit of that and looked up the resistivity of copper, for instance? I think,
Yep.
yeah, we've done that. The resistivity of silver, I think, is smaller. I think silver is a very, very good conductor. Copper is too, but I don't think it's as good as silver. I forget where gold is in there, but we could look it up. It's in your chapter someplace. We've talked about it, but nevertheless, there is resistance, and so why don't we just make up something? So, suppose you had a 90-volt battery, and the total resistance in this loop is 1 ohm. Well, you could get the current, this clockwise current. What would the current be if you had 90 volts and a 1 ohm loop? Current would be
90, 90 amperes.
90 amperes. Be 90. Now, how could you get a 90-volt battery? Well, one way is you could go and buy 10 9-volt batteries and put them in series. Actually, they'll clip together. You clip them, but you clip the plus to the minus. It's kind of hard to clip the plus to the plus. They don't clip. But if you have a, you know, those little 9-volt batteries, the little plus thing fits right into the negative thing. And
Like this.
Yeah.
yeah, he's doing it. He's doing it. See there? But you all know you could put them in series. You could have 10 9-volt batteries in series, and you'd have 90 volts, wouldn't you? Yeah, you'd have 90 volts. And if you had 1 ohm in there, you would have 90 amperes. Okay. So what? Well, let's make a little larger magnetic field here for excitement. Suppose you had a magnetic field of I don't know. We'll make something up. We'll just say 6 Teslas. Now, how are you going to get that? Well, you could get it with permanent magnets, or you could get it with an electromagnet. You can make magnetism with coils of wire. Like a solenoid, for instance. A solenoid will create magnetism inside it, or a circular loop of so many turns. Yeah, we could figure some way of getting these magnetic fields going into the board there.
Professor.
Yes.
Um, since the current's going the opposite direction, is the magnetic field still going into the board?
Yeah.
Okay.
The current's going clockwise. The magnetic field's going into the board. Now, I don't know about the force yet, or the velocity. We're working on that. That was from the 1346. We're doing a rail gun right now, just for fun. But we can figure out if there's any force on this connecting rod. See, it can slide. It can slide on your rails. These are connecting rails. These are the rails. And this is the rod. And let's use this Lorentz equation. By the way, that's spelled Lorentz. The Lorentz equation, which we know and love. Yeah, here we go. There it is. Now we've got an L this time going down, because L is always in the direction of your current. It's going down. Yep. And B is into the board. And if you cross, hope you can read my writing. If you cross L with B, I think you get a force going to the right, don't you? L crossed with B. Yeah, you get a force going to the right. It's right-hand rule. I'm gonna wait for a tiny minute for you to mull that over. I want you to understand that that L going down, cross product with the B going into, gives you a force going to the right. And I'm gonna wait till I hear an uh-huh.
I understand.
There's one uh-huh.
It's the force is orthogonal to
Yeah, they're 90 degrees.
okay.
I need another uh-huh.
Yes, sir.
Yeah, there's one.
Yep, got it.
We
It took me a
got
while
it.
to figure out how to put my hand so that it would work like that. Yeah.
Yeah, you got to use the right-hand rule. I wish I could be right with you in person so I could take my right hand and show
Yeah.
you.
Okay, sir.
Yes.
So we would put our thumb on the arrow going down the rod. Our fingers then are going into the board, and then that is the direction of the force.
Here, let me do it. Let me do it. First of all, you got to have a right hand. Okay, now this is my right hand. And this is my first finger. And this little guy here is my second finger. And this is my thumb. And you got to have them like that at right angles. Now you take this first finger, which goes down. Oh, gee, this is so awkward. First finger goes down. B goes into the board, and your thumb.
Yeah.
The thumb goes that way. Let me stand over here, but I think you can see it better if it's so awkward. All right, now this right here is our first vector. This is our second vector. This is my first finger. It's got to go down. This is my second finger. It's got to go in. By the way, do not practice this. Do not practice this on the freeway when you're driving along.
Okay.
Yep.
You'll have road rage. See? Okay, now first finger is going down, B is going in, and the thumb tells you on your right hand it's going to the right. Well, there's about 4 or 5 right-hand rules. I don't even like that one, but if you like that, do that one. We could explain this with minus J cross minus K, and J, that's equal to a positive J cross K. The two minuses cancel, and J cross K is equal to I. The way it works is I is equal to J cross K. Some of you might,
Negative J and negative K, right?
yeah, but the two negatives cancel and give you a positive.
Okay.
So it's equal to a positive J crossed with a positive K, and I is equal to J cross K. Some of you might like that better. That might make more sense. But whatever it is, there's a force on this connecting rod going to the right, and this thing will just take off. It will just take off. Now here's a word of warning. Mr. Griffin did not tell you to go home and build one of these rail guns. Somebody could get hurt. Mr. Griffin did not tell you to go home and build that rail gun. We're talking about it. Okay. All right, well then let's figure out what it is. Here we go. The current we decided was, I think, there it is, 90 amps.
Yeah.
we've got our current, and the length here of between the rails is 0.04 meters. And then the B is 6 Tesla. I just made that up, but that's okay. And we're going to get the force. Let's give this thing a mass too. Let's say the mass of the rod is, I don't know, 0.100 kilograms. That'd be 100 grams. No, that's too much. I make it point 0.01. Make it 0.010 kilograms. You know what that is? That's 10 grams. Did you know a nickel weighs darn close to 5 grams? So that what that is, this rod has the weight of 2 nickels. If you don't believe me, get your kitchen scale out and put a couple of nickels on there, and it'll weigh 10 grams. Dang close. Now that doesn't hold true for dimes and quarters. A quarter does not weigh 25 grams, and a dime does not weigh 10 grams, but a nickel does weigh about 5 grams. Okay, so here we go. Oh, I never did do this. We're going to find our force acting. Here we go. 90 times 0.04 times 6. Did you get 21.6 newtons acting on that connecting rod?
Yep.
Yes.
Yay! Now we're going to find the acceleration of your connecting rod. Now here's an equation. I wonder if anybody's ever seen this before. What's the name of that equation?
Newton's law.
Yeah, Newton's second law. Well, let's do it. We don't need this summation. There's only this one force acting on it. It's 21.6 newtons, and the mass is 0.01 kilograms. So we're going to get the acceleration of our connecting rod. Okay, I can do that. 21.6, and what would you do? Divide by 0.01. Did you get an acceleration of 2160 meters per second squared?
Yes.
Yep.
Yes.
Hey, that's bigger than the acceleration of gravity. You know what gravity is? It's 9.81, right?
Mm-hmm.
Like, holy cow, that's 2000 and something. That thing really takes off. That's why I'm telling you not to build this thing in your garage this weekend.
But extra credit though, right?
Extra credit if you can.
Yeah, extra credit if you can, right?
If you live through it. No, I don't want I don't want anybody hurt. Okay. All right, now we just talked about rail guns, and the book tells you about them on page 598. You could read more about them if you're interested. But I'm ready to move on now. And the next topic is going to be the magnetic field inside a wire, but we'll stop if anybody has a comment or question. Gee, it's awfully quiet. I guess you're all okay and you understood that all right. All right, we're going to talk about the magnetic field inside a wire. So I'm going to erase this. You better speak up if you wanted to ask about it. Okay, too late. Now, we already have an equation for outside a wire. Outside a wire, it goes like this. I've talked about this. There it is. And that's what it is outside a wire. But inside of what we haven't talked about it. Now it's in your book. And let me tell you where it is. It's in your book and it's on page 557. See here, let's look at a wire. Here's you're looking at a cross section of a wire. And let's say you have current, say you have current coming out. The current's coming out. Put your thumb along the direction of the current, and you know there'll be a magnetic field outside the wire given by this equation. And you could find that magnetic field anywhere you wanted to. Now it gets smaller as you get away from the wire. See, this R is the distance that you go to wherever it is you want to calculate your magnetic field, and it gets smaller and it gets bigger and it reaches its maximum right here. But what about inside the wire? Is there a magnetic field inside the wire? And the answer is yeah, there is. There's a magnetic field inside the wire, but this is not the equation for it. That equation is for outside the wire. Well, let's do inside the wire. Inside the wire, we're going to use Ampere's law, and we're going to find out the magnetic field inside the wire. Well, the way you do that is you make an Amperian path. I've told you about that. There's our Amperian path. It sounds like something out of Star Trek. There's our Amperian path. Sort of messy, but anyway. Okay, and let's write Ampere's law now. You guys all know it by heart. I could wake you up from a sound sleep, give you a pencil and paper, and you could scribble down Ampere's law just like that, because you know it. It's just part of you. And you know how it goes. It goes like this. This circle represents your Amperian path. I forget whether they use ds or dl, but it doesn't matter. It's just a dummy variable. There it is. Now you got to understand though, this I is the current that's enclosed in your Amperian path. We could put a little ENC there that stands for enclosed. Well, let's write it. We'll just write it out. It's the current that's enclosed in your Amperian path. Okay, well, here's your magnetic field. We know it's going to be going like this because you put your thumb there and you'll have a magnetic field.
Professor,
Yeah, go ahead.
your microphone's doing that weird thing.
Oh, here, let me plug it in and try again. Testing 1, 2, 3.
There we go.
It's better. Good. I won't.
Thank you.
Thank you for telling me. Okay, now what we're going to do is we're going to pull this B out because it's constant around this Amperian path. And if you integrate your ds here, well, that's just the circumference of a circle. So what you got is B 2 pi r. Why don't we call the big distance for the whole thing big R? The radius of your wire can be big R, but this little r can be the radius of your Amperian path. Okay, and then this is going to equal mu sub O times the enclosed current. Well, you see, we just want the current that's in here. And what that's going to be is, it won't be the total current because see, there's some current here outside your Amperian path. It'll be the total current times the area inside the Amperian path divided by the total area. That'll be pi little r squared divided by pi big R squared. I don't know if that made any sense, but the current enclosed in that path is not the total current. It's proportional to the areas involved. Here's the area inside your Amperian path. Here's the area outside. The pi's cancel. You can see that. You can get rid of them. You don't need them. And here's the bottom line. Bottom line is the magnetic field inside a wire is equal to mu sub OI. When you put that R in the denominator, it cancels with that R square, and you'll just have a single R in the numerator, and you'll have that 2 pi has to go in the denominator, and there's a big R squared. I think we're done. Unless I've screwed up my algebra, I think we're done. That's it. Now let's look and see if that's the equation the book says. This is on page 557. And I'm going to look it up and see how we did here. Magnetic field inside. How about that? There's a magnetic field inside the wire.
Professor Jeff has a question.
Yeah, go ahead. Yeah.
If B is counterclockwise,
Yeah.
I is out.
Yes.
What would the direction of F be?
We don't have any force this time. Tell Jeff there is no F because we don't have any, we're not calculating the Lorentz equation for the force. Now, if there was an outside magnetic field, there would be a force on that wire, but there is no outside magnetic force coming from something else. Tell him that. We're looking at page 557. We're not calculating force, Jeff, but that's a good question. Let me see if I can find this. 557. By Jove, there it is. And here's what the book says. This is the book. The book says on page 557, they said B is equal to mu sub OI R 2 pi A squared. You know what, they, instead of calling it big R, they called A the radius of your wire. But you know what, that's the same thing as what we got. Look.
Wait, wasn't R on top as well, also squared? Oh no, never mind. It got canceled out. Yep.
It canceled out.
Yep.
Yeah, but thanks for asking. Very good. Well, now we know there's a magnetic field inside wires even. Wow. How about that? They even have an interesting graph on page, let me show you that. On page 558, they plot up a graph of your magnetic field. They plot up your axis like this and this. And all the way up to this value here, it's a constant slope. This graph is on page 558. Do you see that magnetic field is directly proportional to R? We'll put R here, and we'll put your magnetic field here. And all of these are constants. Every one of these is a constant. So you just have B is some constant times R. It's a straight line. But after you reach that, then this This equation gives you your magnetic field outside the wire. Now we're outside the wire, and you'll have a graph that tapers off like that. You'll see that graph on page 558. That's the magnetic field inside and outside a wire. Well, let's see. So far, we've done this wonderful problem here. We've talked about rail guns. We've talked about magnetic field inside a wire. Now, this is a review thing here. The force between parallel wires. We probably should do that. It won't hurt us any to review what we've learned. So go ahead.
One quick question about the force outside of the wire.
Yeah.
When we're calculating the force outside of the wire, are we doing is R the distance from the middle of the wire
Yes.
to the point, or is
Yes.
it the distance from the edge of the wire to the
No,
point?
it's from
Middle
the
of the
middle.
wire. Okay.
But
Okay.
we are not calculating force. We are calculating magnetic field. This is not.
Yeah.
You understand that. You
Yeah,
said
yeah.
force, but I knew what you meant. But yes, we're calculating all these distances here from the center of the wire. Thank you for asking. Okay, I'm going to erase all this, and we're going to talk about force between parallel wires now. Unless somebody else has a question or comment. Well, okay. We'll say goodbye to that for now. And you do have a homework problem on content. You'll find it. I think I'm going to sneeze. I feel a sneeze coming. Maybe not. We'll see. Okay, here we go, guys. Let's suppose you had a wire that was 1 meter long, and another wire very close to it. Why don't we put these wires 2 centimeters apart? That would be 0.02 meters. Let's have them go in the same direction. We'll have the current, but let's have different currents. That would be fun. Let's say this is a 5 amperes, and this is 2 amperes. There we go. Now, let's talk about the 2 ampere current. Put your thumb along that current. This is a review, but I think review is good. Maybe going over stuff that we're supposed to know, right? I think it won't hurt us any. Put your thumb along that current, and I think you'll find there'll be a magnetic field acting on this wire going into the board. And let's stop and get that, shall we? Use your Musabo eye over 2 pi r and get the magnetic field. I'll wait. Find the magnetic field acting on that wire there. It's coming from the 2 amp wire. Okay, well, let's see. I'm doing it now. You know what I got? I got 2 microteslas acting into the board where that wire is. And I'm waiting for an
I got
Yep.
the same thing, but I do have a question. So
Sure.
we used the 2 amp value for I because we're looking for the magnetic field. I'm a little confused about that part.
Well, see,
Uh,
there's a magnetic field caused by the 2-amp wire. It's coming out of the board over here and into the board over here. If you want to know what it is where that wire is located, you have to use the 0.02 right there. It's pretty big. It gets smaller as you get further away.
Okay.
We're not confused, are we?
I don't think so. I think
Would that not be 0.2 microteslas?
I'm getting 2 microteslas. Let me do it again.
Because I'm getting 2 to the negative fifth.
Okay, I could be
I'm
wrong.
getting the negative fifth as well.
Yeah, me
Hey,
too.
I see a thank you point on the way. Let me try it again. I think you guys are right. See, that's what you guys are for. I need you guys. It's 2 to the minus fifth. So if you made that 2 to the minus 6, make that smaller, this is going to be 20 microteslas, huh? Like you guys said, that's. I'm going to put a couple of thank you points up here for you guys. You are one smart bunch of students. It's 2 to the minus fifth, and I was wrong. And you guys were right. Are we okay now, though?
Yep.
Was that a yep? Okay,
Yep.
good. Excellent. Okay. And now we're going to calculate the force on this 5-amp wire. Well, the way you do that is IL cross B. Now the L is going up and the B is going into, and when you cross that, you'll get a force going to the left using the right-hand rule. I can try to go back through that, with my right hand if you want me to. But I'm going to get what that force is. Here we go. You take the 5 amps times the 1 meter times 2 10 to the minus 5. And we're going to get the force on that, the force on this wire. Here goes. Did you get the force on that 5-amp wire of 100 micronewtons?
Yep.
Actually,
Sure.
mine says 1 times 10 to the minus 4 newtons. I'm just showing off here, showing you guys that I can write it as micronewtons. Okay, now let's do this other wire. Okay, this time put your thumb along the 5-amp wire, and you'll discover that the magnetic field on this wire is coming out of the board. And it's equal to mu sub O times 5 amps divided by 2 pi 0.02. And it's bigger. Okay, let's do that. See if I can do that one right. I'm getting instead of 20 microteslas, I'm getting 100 microteslas. Does that sound right? Does that sound right?
I got something.
Let me do it again. So something went wrong. Let me try it again.
I got 50.
I think 50 is right.
That's what I got.
I think I pushed the wrong button here. By Jove, I got 50. I don't know what I did. This magnetic field is 50 microteslas. Now we're going to get the force on this wire. Well, here we go. The force on this wire will be the current in that wire, which is 2 amps, times the 1 meter, times the 50 microteslas. I probably should have written it out. Here, let me write it out. It's IL cross B. It's 2 amps, 1 meter, 50 microteslas. Okay, I'm going to do that. Man, I can do that in my head. I'm coming up with a force. I'm getting a force of 100 micronewtons. You know, it's the same as that force there. They're equal and opposite. It's a Newton's third law deal.
Are these wires attracting each other or repelling each other?
They are attracting each other. Thanks for asking. See, the force on this wire, the one on the right, is going to the left. The
Yep,
force on
okay.
the other wire is going to the right. Now, let me show you why. Because on this wire, L goes up, but now the B is coming out. Now, when you cross that, you'll get a force going to the right. The right-hand rule says up, cross without gives you a force to the right, according to the right-hand rule.
Isn't I the thing that's going up, not L?
Yeah, now here, thank you for asking. I and L are the same direction. L is a vector,
Oh, okay.
and it's in the direction, here's your L. There you go. L is in the direction of your current. Here's your current.
Okay.
Current's going that way. L is going that way.
I think it's that L denotes the direction of I.
Yeah, L denotes the direction of I. That is correct.
Okay.
Good going. Well, I wonder if anybody has any trouble with that. Any questions on that? Okay, well, we're going to talk about chapter 14 then, if you guys are happy with that stuff. I think it's time to talk about this chapter 14 a little bit. The title of the chapter is Magnetic Induction, I think. Let's see. Chapter 13. Yeah. Well, no, wait. No. What I want to talk about is chapter 14. Yeah. We've talked about chapter 13. Chapter 13 is Faraday's law, and we've talked about it. Motional EMF. Yeah, that's right up our alley. You know, though, I haven't told you about motors and generators. Maybe we should, before we launch into chapter 14. Yeah, I need to talk about motors and generators. Okay, but I'm going to erase that if you guys are happy with all that. That was sort of a review. Okay. Well, we've covered a few different topics. We did this one here, the force between parallel wires. We talked about that. There's something else in this. I think it's chapter 12 about the 3 kinds of magnetic materials. I really need to tell you about that. Let me find that just a minute. Sorry to be skipping around like we have been doing here. But yeah, here we go. This is on page 565. there are three types of magnetic materials. Three types of magnetic. Usually it's solids. However, you can have water has magnetism. We'll just say magnetic materials. There are three kinds, and I'm just going to give you a quick talk on those. There's diamagnetic, there's paramagnetic, and there's ferromagnetic. Three kinds of magnetic materials. And they have a list of some of the ones on page 567. They have a pretty big list there of different ones. They have, well, even air and water are in the list. And they have aluminum, chromium, magnesium, tungsten, copper, carbon, hydrogen, nitrogen. Now, the way they taught me in school is that all materials have this diamagnetic property. I think there's other materials besides just this list here. What do you got there? About 10 or 15 different ones. And it all has to do with magnetic dipoles. See, if you have a, do you remember that equation where we had the torque on a current loop was this thing they called the magnetic dipole moment, I think is what they called it.
Yeah.
It's I times A, and it's talking about the current going around a loop. Well, it turns out that atoms are like that. If you take an atom, say maybe, I don't know, hydrogen atom, it's got a single electron that zooms around the nucleus, which is what, just a proton for hydrogen, huh?
Mhm.
And it has a magnetic dipole moment. You could think of it as a current. I mean, that is a charge and it's moving, and it's not much current because it's only a single electron, but there's a current there and there's an area there. Hydrogen atoms have, it's a very tiny area, but we're talking about all matter has dipole, magnetic dipole moments. And so what happens is when you superimpose a strong magnetic field on these atoms, I'm not sure I understand it, but you get an opposition, kind of like Lenz's law. Here, let me put it this way. Let's say you have a solenoid. Okay, here's your solenoid. You all know solenoids are like that. And you have current in it, and you have a magnetic field inside. Now, if you take a diamagnetic material, like for instance, well, they have bismuth in here. It's diamagnetic. I don't know if I've ever had any bismuth. But they have copper. Copper is diamagnetic. Lead and mercury. Carbon. Carbon's diamagnetic. But anyway, if you put if you have a solenoid, you know there's a magnetic field inside the solenoid. If you put a diamagnetic material inside your solenoid, it reduces the magnetic field in your bismuth or copper or whatever. It's not, the magnetic field, it gets smaller. So you have this here. We learned about solenoids. It goes like this. It's equal to mu sub O. What is that? Permeability of free space times N times I. But inside inside your solenoid, the magnetic field is smaller. It's actually equal to mu Ni, where mu is equal to mu sub O minus, and I don't want to foul this up, it's equal to mu sub O minus a number. And for bismuth, it's awfully small. I'm not going to test you on this, so probably you should start forgetting what I'm doing right now. And we need to go on to something that you're going to be tested on. But I just wanted you to know. But see, the magnetic field will be smaller. Now for paramagnetic material, what happens is the magnetic dipole moments start lining up. They start lining up, and this number is bigger for things like maybe calcium, chromium, magnesium. This number is bigger. And for instance, for what is it, magnesium, you would have to add you don't subtract the magnetic field inside of that magnesium is actually bigger than the magnetic field of your solenoid because the atoms line up their dipole moments. And finally, there's the ferromagnetic materials. These effects here are very small. Do you see this number here, -5? You could probably forget it. It's so tiny. But the ferromagnetic materials, I'll let you read the book, but I'll tell you this. They increase your magnetism by factors of sometimes 1,000, okay? We're talking, that's what magnets are made out of. You know, the magnets that you played with as a kid, north-south magnet, they're made of ferromagnetic material, and they have something in them called domains. And they all connect with one another. Read the book. I'm through with that. I just told you about the 3 types of magnetic material. I haven't neglected you. But they make permanent magnets out of the ferromagnetic materials. But there's 2 other types. Okay, we're going to launch into chapter 14 now. And we've got about 15 minutes or so. Hey, wait a minute. I got you till 4 o'clock, right?
Yep.
Okay. Well, go with me to chapter 14, and we're going to talk about yeah, it is. It's 14, yeah. We've hit most of these topics that I think are important, but now we're going to go into chapter 14. And the title of this chapter is Inductance. And we're going to study something called inductors. Now, you know, we have studied resistors. We have studied resistors. We have studied capacitors. And you know a lot about those. We've done homework problems, we've done lab exercises, but right now the topic is inductors. This is the symbol for an inductor. The symbol for this is C for capacitance. It's L for inductors. Don't ask me why they picked L. I can see R for resistors because there's an R right there.
Mm-hmm.
I can see C for capacitors. There's a C right there. But I don't see any L's in that inductor, do you? Of course, they couldn't call
Yeah.
it I because
Yeah.
we use I for.
They ran out of letters, but even with L, then still
Yeah.
run out of letters.
Well, that's just the way it is. Okay, now they have something called mutual inductance, but I'm going to launch right into self-inductance on page 640.
That the L comes from Heinrich Lenz.
Oh, maybe Lenz's law. You think?
Yeah, I think so.
Really? I didn't know that. That's interesting.
Uh,
That's fascinating.
yeah,
It could come from what's Lenz's first name?
Heinrich.
Oh, Heinrich. Okay, cool. All right, I like that a lot. Maybe that's in honor of. See, I didn't know that. That's in honor of Lenz and his law. All right. Well, let me tell you this. Your Faraday's law, we all know and love. It goes like this. Now, if you have more than one loop, then you have to, for every loop that you have two loops, you have to double the magnetic flux. There you go. That's Faraday's law. But I want to tell you something about flux. Flux is proportional. I don't know the symbol, but it's definitely connected to magnetic field. Well, you know it is. By definition, magnetic flux is this here. If you don't need to integrate it, sometimes it's just B times A. But it's definitely proportional to B. In other words, if you double the B, you double the magnetic flux. If you triple the B, well, you triple the magnetic flux. And B is directly proportional to your current. B is directly proportional to your current. Like, for instance, here, let me show you some of these equations here that you know and love. Yeah, here we go. There's this one. Haven't we just been using that? Notice that B is directly proportional to the current. If you double the current, you would double the B because these are all constants here. How about this one? This is the one that I gave you on your, what do they call it, the virtual lab thing that I gave you, that one of my excellent students pointed out that I forgot to double the last answer, and my answer was only half of the correct answer on that lab. My smart student figured out that I'd forgotten to double it, which means I got to go back and give more points to the people that I robbed, because I think they got it right. And I got the final answer. I did everything right on that, but I forgot to double the answer. So when I screw up, you benefit. Okay, now I want you to look at this equation here. Notice it's directly proportional to the current. You know what that was? That was the equation for a short wire. This is the equation for a long wire. We've studied those.
Professor, this is the interpreter. I think your mic is starting to get staticky again.
Oh no. Okay, well here, let me thank you for asking me. Oh gee. Your default microphone has changed to microphone and will
There
not.
you go.
We can hear you.
Good, excellent.
Thank you.
Thank you. Please inform me. Now this is for the a circular current. If you're in the center of a circular current loop, the magnetic field is equal to this here. And if the current loop has n turns, so you have to multiply by n. I could keep on going here, but you get the picture that magnetic field is directly proportional to the current, to the current, to the current. The rest of this stuff is all constants. So therefore, you could write this, you could write Faraday's law like this, as some constant here times di dt. Since the flux is directly proportional to magnetic field, and since magnetic field is directly proportional to current, then d phi dt is directly proportional to di dt. Does that kind of halfway make any sense to anybody?
Those on the right. They are the Lorentz and Savart equations, right?
Yeah, for long and short.
The Biot-Savart, here, I'll write that for you also. The Biot-Savart goes like this. I think they use an A for some reason. I believe, unless I've screwed up, that is the, there's no A there. That's the Biot-Savart law. But again, I want you to notice that the magnetic field is directly proportional to the current. The flux is proportional to the magnetic field. Magnetic field is proportional to the current. And so there's some constant here. Don't know what it is, but you could stick that in there. Hey, let's give it a name. I know what we could do. We could call it L. We could call it L. We'll give it a name. We'll call it inductance. And so your voltage is equal to minus L di dt. It's a form of Faraday's law. If you understood all that, we're going to come up with the equation for inductance now. Here goes. I just need some room here. And this will launch us into this chapter 14. Right now, for those of you that are just waking up from your nap, how am I doing on time? I'm doing pretty good. It's 2:15 now. Gee, I shouldn't have erased it. Let me put it here though. We've got voltage is equal to minus and we also have another way of writing it now. And so what we're going to do is we're going to do some algebra on that. You see those DTs there? Just lop them off. We don't need them. Hey, those minuses, lop those off. See if you can get to here with me. Can you make it from here to here? Now what we're going to do is we're going to integrate both sides. And what you'll get here is just n phi sub b equals Li. And now we're going to get this mysterious thing that they talk about in chapter 14 called inductance. That's the name of it. It's called inductance, or that's the symbol for an inductor. And it's equal to n phi sub b over I. There you have it. That's a symbol for an inductor. Let's look at the units of
What's
inductance.
Professor?
Yeah.
What's that subscript next to the flux I?
Next to the I,
The flux.
the flux, that's a B. That's magnetic
Okay.
flux. Because remember, there's also electric flux that we studied long ago when we were younger and better looking. Remember the electric flux?
Yeah.
Yeah, we studied that long ago. But this is magnetic flux. Now we're going to look at the units. Now N is unitless. It's just a number of terms that we have. It doesn't have any units. I know what magnetic flux is, though. It's, well, it's Tesla meters squared. It's B times A. And I know what I is. It's amps. So inductance, you know, an inductor is one of these little guys. And this thing is inductance. It's equal to Tesla meter squared per amp. They have its own name for that. It's called the Henry. It's in honor of a famous guy named Henry. I forget his first name. But what a Henry is, it's a Tesla meter squared per amp. Now we can doll that up and make it a little different. If you remember what a Tesla is a Newton per amp meter. And so you have a Newton per amp meter, you have another amp and a meter squared. So we're looking at a Newton meter squared. Hey, you know what? We can cancel out that square meter and get rid of that meter. And you have a Newton meter over amp squared. But you know what an amp is? An amp is a coulomb per second, isn't it? And a Newton meter per coulomb, that's a volt. Because a Newton meter is a joule. And so what you have here is a volt. You have a volt second per amp. Did I do that right? Gosh, I don't know. We better double check this and make sure I'm not lying to you. We're in chapter 14, and we're trying to find what the heck a Henry is. And if I did that right, it's a volt second per amp. Did they ever tell you that in chapter 14? I can't find it. We might have to just work it out for ourselves.
It's a volt second per amp.
I think it is. Now
Yeah.
guys, we've had a volt per amp before. Is there anybody out there that remembers what a volt per amp is?
Is that a Tesla?
Nope.
Um,
I'll give you a hint. It's voltage. See, these are units here,
mhm.
but it's
Oh.
voltage over current. What is V over I?
The current.
R.
Yeah,
Resistance.
Yeah, R resistance.
yeah.
Yeah.
So this is a ohm, isn't it?
Hmm.
So what we have here is an ohm second. You might like this.
Hmm.
A Henry, I like it. A Henry is an ohm times a second. That's what a Henry is. Okay. I'm going to tell you one more thing, and then I think I'm going to just let you guys look up your homework and work on it. And we'll see you on Monday at 1. Why do we have inductors? I mean, what do we need them for? Well, I need a little room here to operate. It's for the same reason we have capacitors. What does a capacitor do for us? Does anyone remember?
Stores
Store
energy.
power.
It stores charge, and it stores energy is the right way of putting it. I guess it could provide power for a short period of time till it drains out,
Mhm.
but it stores. Capacitors store energy, and they store them in electric fields. You know, you can store energy in gravitational fields. All you have to do is get your water tank here. Here's your city water tank. There you go. And a pump. You need a pump, and you need to pump the water up into the tank. There you go. Fill that tank, and you're storing that water up high, and it gives you a lot of pressure when you open the valve down here, and you're storing energy. Whenever you lift a body, you're doing work on it and you're storing energy. Well, capacitors store energy in electric fields. Inductors, they store energy, but in what kind of fields?
Magnetic.
Yes, they store energy in magnetic fields. That's exactly right. And the amount, you might remember this. There was an equation for capacitors. Let's see if I can remember how that went. The energy in a capacitor was 1/2 CV squared was one equation. There was another one that went 1/2 Q squared over C, and a 1/2 QV. I think there were, those are all good. Does that ring any bells for my students out there? You remember that, the energy stored in capacitors?
Yes.
Yes.
Yeah. See, you could check the units on this. This would be coulombs per volt, which is a joule per coulomb. Coulombs cancel and you get joules. See, all of these will give you joules. Well, what about inductors? Well, the equation for inductors is on page 645. I think I'll save it till next time to show you where the heck it came from, but it's 1/2 Li squared. You'll discover something interesting about energy. Not always, but a lot of times they have 1/2 something squared. See, in this case here, they have 1/2 all over this constant times Q squared. Here you have 1/2 some constant times V squared. Have you ever seen this one here? 1/2 mv squared. What's the name of that energy?
Kinetic energy.
Kinetic.
Kinetic.
Kinetic energy. How about this one? There's no 1/2 on this baby. It's just MC squared. What happened to the half? I'll let you worry about that. But energy is oftentimes 1/2 something squared, and that's true for inductors. Let's look at those units a minute. This would be 1/2 is dimensionless, and inductance is in henries. Current is in amps. Remember, after much work, we found out that a henry is an ohm times a second. And an amp is a coulomb per second, but it would be coulomb squared per second squared, wouldn't it? So let's see what you get when you do that. Let's see if it comes out to be energy. Well, one of these seconds you can get rid of. And we have, let's write it this way. We have an ohm times a coulomb per second times another coulomb. What is a coulomb per second? Does anybody know?
Volt current.
It's a current. It's an amp. It's an amp. So what we have here is ohms. I should have put brackets on those. We have ohms times amps times coulombs. I really need to put all of my units in brackets because it can get confusing. There we go. Okay. Does anybody know what an ohm times an amp is?
Volt.
It's a volt. So what we have here is a volt, which is a joule per coulomb, times a coulomb. By Jove, the coulombs cancel and you get joules. So 1/2 Li squared is very definitely equal to joules. It's a unit of energy. It's energy stored in your inductor. The more current you have, the more energy is stored in the inductor. Well, do your homework, read your chapter 14, and we've had fun. And that's where we'll be on Monday. We'll be in chapter 14. Are there any questions on anything that we've done today?
I have a question, but it's unrelated to this class. So
Okay.
if anybody has any other questions, I can go last.
Go ahead.
So I'm taking Intro to Electrical Science with Professor Weigel,
Yeah.
and
Yes, it's Weigel.
Weigel. And we built this circuit, this breadboard, which has an op amp, and it's supposed to flash this LED.
Yes.
And he told me that the capacitor I have on here may not be correct, and I'm looking for a 0.1 microfarad capacitor.
Okay.
And I have this handy box full of capacitors, and I'm trying to figure out which one might be the 0.1 microfarad. I pulled what I believe to be a monolithic ceramic,
Okay.
number 104, and they look like this.
Okay.
And
Now you're trying to make a 0.1 microfarad?
yeah, in this box I have here says that I've got a 0.1 microfarad, but I can't find it in
Well, I'll tell you this, it's pretty small. 0.1 microfarad's a pretty small capacitor. It's just a little guy with 2 wires sticking out of it.
that look like this.
They're usually brown. Yeah, they look like those.
Okay, so I just need to find the one that has the correct number.
Yeah,
Okay,
He said that they're usually brown, apparently.
they're usually brown. Yeah.
okay. All right, well, that helps.
Okay. Well, good luck.
I appreciate it. Thank you.
Anytime. Anybody
Yeah.
else?
Scott, so you're taking Intro to Electrical Science right now?
Yes.
I wonder how that's gonna go because I have to take it over summer, and
Oh.
it's online.
Yeah, he's being very relaxed about the due dates, but it is way more difficult online.
Oh, yeah.
Yeah, we'll see how it all goes.
The
Yeah,
thing
it's-
about, guys, the thing about Mark, though, he's a computer guy. He's not like me. He's younger.
I had him for computer programming.
Yeah, he's younger. He's okay with computers. He's not an old guy like me, but I'm doing the best I can.
Well, thank you.
Mr. G,
Anybody else?
Mr. Griffin,
Yes, Kristen.
this is Melissa.
Well,
I cannot.
I'm sorry, Melissa.
It's fine. You had a 50-50 chance. I cannot read what is underneath where you're talking about the Henry and the amps squared
Yeah.
went to an ohm, amps, coulomb. What is that underneath that? I cannot read that.
Oh, I'm sorry. That was my bad writing. Was it down here?
Bring it up. Bring
Where's-
your marker up. One
Bring it
more
up.
row. This, whoop, in the middle, down.
Right here. Right here.
This. I cannot read that.
Okay. Why don't I write it out to where you could read it? That'd be nice. Now, a Henry, we think, is an ohm times a second. And an amp is a coulomb per second. But see, it's squared. Sorry to make my S's different there to confuse everybody. I think that's what it said, Melissa. But can you see one of these seconds will cancel? In fact, you could write 1 amp as a coulomb per second and the other amp as just an amp. See, this is an amp squared. So you got an amp squared, there you have it. One of the seconds cancel. And what you have is an ohm times an amp. I got kind of sloppy there.
I'm the coulomb.
Ohm times a coulomb. And an ohm times an amp is a volt. And a volt is a joule per coulomb times a coulomb gives you a joule. There you go, Melissa. It worked.
Thank you.
Anytime. Anybody else before I click on this end meeting thing here? Well, okay. I've got my pointer on end meeting. 5, 4, 3.
See you
Two.
on Monday.
I'll see you on Monday. Bye-bye.
Bye-bye.
Bye-bye.